Okay, I think we'll get started. If you're coming from the GNL project, I encourage you to look at the introductory video to this playlist to make sure that this is the right course for you. All right, so we're going to talk about a really important concept here, simple harmonic motion. One of the most important models in physics. Oftentimes, anytime there's any kind of oscillatory motion of an object, physicists would first try to model that as a simple harmonic motion. And this is the type of motion that the spring mass system undergoes in its natural oscillation as we let go and let the mass oscillate back and forth. Okay, so the prototypical model here is that we have a mass on a spring, so we have a mass and a force constant there, and together these determine the frequency, the circular frequency of this system. And we know that the circular frequency is 2 pi times the linear frequency, and the linear frequency is 1 over the period. So if we know the mass and the spring constant, we can get the period, we can get the frequency, we can get this circular frequency omega. So the whole system is described by just 2 parameters: the spring constant, the tightness of the spring, and the mass. Notice how these go together. If you have the same spring but put a heavier mass, it will oscillate more slowly because mass is in the denominator here. And if you have the same mass and maybe make a stronger spring, then it will oscillate faster because the spring constant is in the numerator. So it's inversely proportional to mass, and the frequency is directly proportional to the spring constant, albeit with a square root. Okay, well, let's connect with something we've talked about before, and that's this energy diagram. So you might remember back a couple of lectures ago, we have a total energy in the system because the energy is conserved, and then we have our parabolic. We know that the spring mass system is described by a parabola for the potential energy. And normally we use a delta, or we were using a delta x here, a displacement from equilibrium. We're just going to let the equilibrium lie at 0, and then the value of x will be that displacement. So it's a little switcheroo here, but it makes it convenient down the way. Okay, so we have talked about that when the mass is pulled all the way back, it stops, right? Let's say we pull the mass back, we let go, it goes all the way across, it stops, then turns around, comes back. Those stopping points occur when the potential energy is equal to the total energy, and the positions there are called the turning points. We're going to refer to this now as the amplitude, and so x is equal to a at this turning point, and x is equal to minus a at that turning point. So that's the amplitude of the swing of this mass on this system. We would need some calculus to actually get this from Newton's laws, so we're just going to be given the formula for the position as a function of time. So we can imagine that the value of x here is going to change with time, and it's going to do so cosinusoidally. So we have cosinusoidal or sinusoidal motion. We have the amplitude times cosine of 2 pi f. So notice this is that omega frequency, the circular frequency, times t, plus a phase shift. And this is just to take into account where we start considering the motion. So the spring could be going forever, and then we start our watch at time equals 0. That's going to determine this shift in its position. So it's not all that important if we're just thinking about this generally. Of course, in the details of the problem, it would be important. But we can think about this as a case where we're just going to pull this guy back and let it go. So we're going to end up pulling it this way, and we're just going to let it go that way. So pull and let go. in that case, the phase shift is 0. So we can take the phase shift to be 0 and still understand everything. It still has is general. Okay, so what do we want? We want the kinematic equations for this. Again, this would be calculus. So we're just going to write them down, and then we're going to look at graph them graphically. So we start with our formula here, but with phase equals 0. Then the velocity is going to be minus 2 pi f times a sine 2 by ft. And if you've had some calculus, maybe you can challenge yourself to figure out why that is the case. This is going to be called Vmax. Then for the acceleration, we have minus 2 pi f squared times the amplitude back to cosine again. So again, a calculus thing, and this is going to be the amplitude max. So the velocity, notice here, the velocity max is not determined solely by the amplitude. It's determined by the amplitude and the frequency. Okay, well, let's sketch pictures of these. So this is cosine for a case where we're pulling it back, we're pulling it this way in the positive direction, and then we're going to let it go. So what does it do? The position starts to move to the negative direction. So we're right here, and then as we get to here, that means we're here. So we're all entirely kinetic energy. And then we come all the way across to here. Now we're at the negative amplitude right here. So from here to here is half a cycle. It's here to here. Then we stop and we turn around and come back, and now we're back to where we began. So that defines the period of this. So the time from peak to peak is the period here. All right, well, let's plot the velocity. So let's do it two ways. Let's just look at the mathematical formula. It's negative sine, so that's what that looks like, right? The frequency arguments are the same, so it's going to be exactly like this, but just shifted like a sine wave. So the period from here to here is exactly the same as here. The amplitude is given to us by this, but let's think of it also physically. So I've pulled this back. The velocity is 0. I'm going to let it go. The instant I let it go, the velocity is 0, and then it starts to take off this way in the negative direction. So from a physical perspective, that makes some sense. Here at Vmax, that's going to be right here. So where our position is 0, we have the maximum negative velocity in this case. Then it turns around and comes back. We're at the maximum positive velocity here. So that's coming back this way through that point. All right, let's plot the acceleration. So the acceleration, again, just mathematically, is negative cosine. And it's going to be just like this cosine, but flipped upside down. And then the amplitude is going to be determined by the A max. So what do we see here? The maximum acceleration in either direction is right when we let go, or right at the turning points, because that's when we have the most stretch in the spring, so the largest force, F equals ma, so that's going to be the largest acceleration. So good. This is another good example where it can be a little counterintuitive. The maximum acceleration is actually when the object itself, the mass itself, is stopped, is not moving. Okay, a little kind of connection here. We know the harmonic oscillator has a linear restoring force. And again, I've switched out delta x for x here, just for convenience. So we have a linear restoring force, negative times the force constant times this displacement. That gives rise to simple harmonic motion. So if we plug that into Newton's laws and solve it using calculus, we get this. The converse is also true. If we have simple harmonic motion, then that means we're coming from a restoring force, a linear restoring force. Okay, now we're going to go into something that actually isn't in the book, but I think it gives us a lot of insight. We're going to plot what's called a phase space. So we're going to plot on the horizontal axis the position, and the vertical axis is going to be velocity. Now, if you were to Google phase space, most often you would find this to be momentum, but velocity is fine here, and we know they're related through P equals mv. So we're just going to use velocity here because we have our graphs and our formulas here. So let's take this case. We're going to start here. I'm going to pull to the most positive direction, and I'm going to let it go. So I'm at the highest x value. So I'm going to put I'm going to put my point right there. Now, as I let go, I'm going to start to move in this direction. That means I'm going to start to move this way on the horizontal graph. But what is my velocity doing? My velocity was 0, and now it is going to go negative. Right? So we're going to start to go negative. Now, as we get to here, I'm at position 0. Right? I'm 0 here, but I'm at the maximum negative velocity here. And then I continue to go, but as I start to go past this point, I start to slow down. So I start to come up this way, right? Less negative as I go more negative in x. So I end up here. That is going to be here. And then here and here. Now you wouldn't know exactly, but it turns out to be an oval. And in this case, I drew it kind of like a circle here. These are different units, so we can't say it's a circle, but it's an oval shape in this phase space. And so this is a nice way to think about the nature of this motion, because we can see it's periodic, right? It just keeps going around in a circle, and we can track at any given point the position and the velocity. Let's try to plot two cases. So let's say the mass is the same, and then we have a K1 is greater than K2. Right? K1 is greater than K2, and we're going to pull it back to the same distance, the same amplitude. So let's just get one of these in here. We'll get K2 in there, let's say. And K2, well, let's do both, I guess, simultaneously. What is the Vmax has the amplitude, which is the same here for both K1 and K2, but the frequency is different because the frequency of K1 is greater than the frequency for K2 because they're proportional to the square root of K. So this implies that F1 is greater than F2. And so we're going to have 2 points here where this is V2 max and this is V1 max. And so then this is going to be for the K1 case, the stronger spring, and that will be for the K2 case. That's if we've pulled the mass back to the same spot. Okay? Let's do one more. Let's take the same mass, but we'll just pull it back to two different amplitudes. So same M and K same, and we'll have A1 greater than A2. So then we have an A1 and we have an A2. Now, the frequency will be the same, but the velocity also depends, the Vmax also depends on A. So we're going to have 2 like this. And the A1, this is V1. Oh, sorry. These backwards. A1 is greater than A2. And this is V1 max. It's a little different than the last one. We have concentric circles here. All right, so that's this idea of phase space. We're going to get a lot more practice with this in class. If you're coming from the G.N. Lewis project, then try to think about this. Tell yourself the story of the phase space. I think this is conceptually the hardest part, but it gives you a lot of insight once you get it understood.